Hi all, today we're gonna go over the Unit 4 test from this year. So this is from May 2025, as you can see. So let's jump right in with Section A. So section A consists of 10 questions with worth 1 mark each. And the general rule of thumb, as I said in previous videos, is that 1 mark means it should take you about 1 minute. If it takes you 2, don't freak out. I mean, some are easier and some are harder, that's okay. But if a question is like 12 marks, it means that it should take you about 12 minutes and so on. Right, now, let's start with the first question. An isotope of astatine has the symbol At213 and 85. So that's the mass number. So 213 is A, and Z is 85, as you can see. Which row of the table shows the number of protons and the number of neutrons in a nucleus of this isotope? So immediately we see that it's either B or D. But D has the mass number there, so the right answer is B, right? Because N, the number of neutrons in a nucleus, is A minus Z, which is exactly 128 in this case, all right? Now, question 2. A capacitor is charging. A graph of potential difference against charge is shown. Which of the following gives the capacitance of the capacitor? Recall that charge is given by, capacitance is Q over V. I don't know why I'm using red. Let me switch to black. So V, the potential, is 1 over C times Q. And here we have the potential plotted against charge, right? So the gradient of this curve is 1 over C. So the capacitance of the capacitor is the inverse of the gradient, right? So the correct answer is D, the inverse of the gradient of the line, which is what I have in my notes. So let's move on. Question 3. A proton is in a vacuum. At the distance r from the proton, the electric field strength due to the proton is 0.77 newtons per coulomb. Which of the following gives the distance r in meters? So this is a little bit more involved. Recall that the electric field strength, which is a vector, but we don't use the hat here, the arrow here, because we don't care about the direction. We only care about the magnitude, which is given by 1 over 4 pi epsilon naught times 1 over the distance from whatever sets up that electric field. So, and this is for point and spherical charges. So R is the square root then of, and I'm going a little bit fast, I'm sorry. What did I write here? Something's wrong. I forgot, I'm sorry guys. E over r squared. And why E? Because this is a proton, right? So the distance from that proton is E over 4 pi epsilon naught, and then the electric field strength. So that's so immediately we see that C and D are completely wrong, and then we can immediately deduce, this is the lawyer's way as I call it, the lawyer's way of solving these kind of questions of section A is to find all the parts that are wrong and end up with the right question. So this is wrong, this is wrong, this is wrong because it has the charge square, so this is correct anyway. But we also saw, using the formula here, we saw that this is exactly the answer because E is 1.6 times 10 to the minus 19 coulombs, the charge of 1 electron or 1 proton. And then 4 pi times epsilon naught, this is epsilon naught, okay? So that's epsilon naught, and this is the electric field. So that's correct. Okay, right. Question 4. In the upper atmosphere, high energy cosmic rays collide with molecules of air to produce muons. The average speed of these muons is v. The average lifetime of these muons is greater than the average lifetime of stationary muons. Okay, which of the following gives the reason for this increase in average lifetime? So this is the concept of time dilation, which tells you dilation with D, I'm sorry, which tells you that moving objects, moving particles in particular, moving particles take a longer time to decay. So if the decay constant is tau for stationary, for moving particles is tau prime larger than t, and the reason is because v is close to the speed of light, so it's approximately equal to c. And actually t prime is exactly gamma times tau, and this gamma is something that is out of scope, but it's good to know. Gamma is the relativity factor, which is 1 minus v over c and the whole thing squared, where v is the speed of the moving object, okay? And this gamma is always larger than or equal to 1, okay? It's equal to 1 when gamma is 0, is equal to 1 when v is 0, okay? But when v is close to c, this gamma is really large, so the answer is c, okay? Hope this makes sense. And by the way, one comment here, v, the velocity of anything in this universe, can never be larger than the speed of light. It's the ultimate limit. So there is an upper limit to speed in this universe. I don't know about other universes, but in this one, that's the upper limit, okay? Now, let's move on with question 5. In large angle alpha scattering experiments, alpha particles were directed at a thin metal foil. The alpha particles were then detected at 4 positions, Wx, W is here, X, Y, and Z. All right, as shown. Where were the most of the alpha particles detected? Remember that most the largest volume of the, the largest volume in the atom is empty. So atoms is mostly empty space. So alpha particles mostly go through. So the correct answer is Y, position Y, which is C, okay? So most alpha particles, so most of them go here, then you have very few that go there, and then very, very few backscatter, as we say, okay? But the answer is C. Question 6, in an electron gun, a current hits a metal filament to release electrons. Which of the following is the name of this process? This is the thermionic emission, okay? So heat provides the necessary energy for electrons to escape the metal. This is similar to the photoelectric effect, but the photoelectric effect takes, in the photoelectric effect, the electrons escape after they receive light, so they get energy from light. Whereas in thermionic emission, they get energy from heat, okay? And then beta decay and ionization are completely irrelevant to this process. Right, so question 7. An electron and a positron collide and annihilate, producing 2 photons. Which of the following is the energy in joules of one of these photons? So we have an electron. Actually, let's use different colors. Let's use, let's use blue for the positive, for the positron, and red, let me erase this, and red for the electron, okay? So this is the electron, this guy comes in, and this guy comes in, they annihilate, so all of their energy gets converted to light, okay? So actually light, let's use yellow, so let's see, yellow, okay? So you have 2 photons, gamma and gamma, okay? So where do they get their energy from? From the mass of these 2 electrons, right? So the total available energy is 2 times the mass of an electron times c squared. This is Einstein's relationship, okay? And this is equal to 2 times the energy of the photons, because you have 2 photons, right? So this gets cancelled, so the energy of the gamma is the mass of the electron times c squared. C is 3 times 10 to the 8, and then squared. So the most, so questions B and D are wrong. Sorry, answers B and D are wrong, whereas A is the correct answer, okay? Because this is the mass of one electron, and this is the speed of light squared. Sorry about that. Siri responded on my computer. So anyway, so let's move on. Question 8. In high-energy collisions, electrons are used to investigate the structure of nucleons. Which of the following is the reason why the electrons need a very high energy? All right, so this needs a little bit of thinking maybe. So the first answer is so that new particles are created. Okay, that's promising. Answer B says so that collisions between electrons and nucleons are elastic. That's wrong. They are not necessarily elastic. Okay. Elastic, by the way, means that things bounce off of each other and no energy is lost. In this kind of processes, some energy is lost in creating new particles, in electrons getting absorbed into the nuclei and stuff like that. So B is totally wrong. C, so that the electrons have a large wavelength. It's the opposite. If you have really high energy, then remember that lambda is the wavelength of matter particles or of electrons is equal to the Planck constant over p, their momentum. So high energy means high momentum, so low wavelength. So C is totally wrong as well. And then D, so that the quark is knocked out of the nucleon. So this is totally wrong as well, even though it sounds plausible. And the reason is that quarks cannot exist alone. So quarks don't exist alone. So the correct answer is A. Okay, new particles are created in processes that kind of resemble this process that we just talked about. Okay, so the energy gets converted into the mass of new particles, pretty much. Okay. Now, question 9. In a nuclear fission reaction, a nucleus splits into nucleus S, a nucleus T, and several neutrons. S and T have the same kinetic energy. T has twice the mass of S. Which of the following is the ratio of momentum of T and the momentum of S? So the kinetic energy of S is PS squared over 2m. Now the kinetic energy of T is Pt squared over 4m, and the reason is because T has twice the mass of S. And then they say that the kinetic energy is the same, so Ps squared over 2m is equal to Pt squared over 4m. M gets cancelled, and then you have Pt over Ps squared is equal to 2. Therefore, Pt over Ps is just the square root of 2, and the correct answer is C. Okay. And now question 10, which seems like the hardest maybe. So, but let's go see it. A model aeroplane is moving at a constant speed in a horizontal circle, and they show you the circle here, okay? F and G are two positions of the model aeroplane. The velocity at F is Vf, and the velocity at G is Vg, as shown. As the model aeroplane moves from F to G, the change in velocity is delta V. Which of the following is a correct vector diagram for this situation? So the best way to think about it is your vectors can be parallel transposed, if you remember. So this is your Vf. So we can kind of grab it. So let's literally grab it and move it over here. Okay. So let's call it this Vf. Okay. Now what is delta V? Delta V, vector wise, okay, is V final. So this is V capital F. Capital F refers to point F, whereas lowercase f refers to final velocity. So Vf minus V initial which is VF is VF capital, that's the final velocity. And then we can say plus the opposite, sorry, what am I saying? V final is V in G. I'm sorry about that. So that's Vg. Okay, the final velocity is the velocity at G, plus the opposite of Vf. Okay, this is how we subtract vectors. We add the opposite pretty much. Okay, and the opposite of Vf is a vector this way. Okay, Vf. So that's actually minus Vf. Okay, so if we add this vector and this vector, we get this vector, right? And that's simply delta V. Okay, do we have anything like that? Yes, we do. See. Hope this makes sense. So let's move on to section B. I'm going a little bit fast because the idea is that this is a walkthrough on a past paper. You can watch my other videos about to learn more about the theory and so on. So here I'm just providing answers and a little bit of, and I explain things a little bit. Okay. Right. 11. A proton enters a magnetic field as shown. And I remind you that if B is shown this way, it means that it comes out of the page, whereas if you have a cross, it means that it goes into the page, and this refers to an arrow pretty much. So if an arrow goes into the page, you will see the tail, which is the X, the cross, whereas if it comes out of the page, you will see its tip, so it's a dot. Right, the proton experiences a force of 6.5 times 10 to the negative 13 newtons due to the magnetic field. Calculate the speed, and they give you the magnetic flux density, which is B. Remember that the force on a moving particle, the force called the Lorentz force, right, of a charged particle moving in a magnetic field is given by its charge times its velocity times B. Here we want to calculate velocity, so force over QB, force is 6.5 times 10 to the negative 13 newtons, charge is 1.6 times 10 to the negative 19 because that's the charge of a proton, so that's coulombs, and B is 0.52 teslas, and if you do the calculation you will find 7.8 times 10 to the 6, meters per second. Okay, draw on the diagram above the path of the proton in the magnetic field, and I remind you that here we need Fleming's left hand rule. So V is our middle finger. Always use the left hand, by the way. This is a common mistake, to use the right hand and then you get things messed up. B is your index finger, and F. So you put your middle finger in the direction of the velocity. So you can't see me, but let's assume I do that. Okay, and then your index finger in the direction of the velocity. Oh, sorry, of B, and then your thumb is gonna point in the direction of the force. Okay, which in this case is down, so the proton will move this way. Okay. Question 12. A student investigated collisions using 3 spheres. The student rolled a sphere of mass 35 grams into 2 stationary spheres, each of mass 37 grams as shown. Okay. During the collision, the rolling sphere was brought to rest and the 2 stationary spheres began to move apart at an angle theta as shown below. Determine the angle theta. So this is a problem where we have to use momentum conservation in 2 dimensions, but it's a little bit simple in that we can only use the x-axis. So what I'm gonna demonstrate and then only show the x-axis. So before we have only this momentum, and after we have a momentum here and a momentum there, which you can analyze into a vertical component and a horizontal component. Notice how the vertical components cancel because they are exactly equal, since the angle is equal and the speeds are equal. So what we have to do pretty much is to set in the x-axis, we have to set the momentum before, let's call it m times v, equal to 2 times the x component of the momentum in the situation after the collision. So let's call it 2 times m prime v prime times cosine of theta over 2, y theta over 2, because this angle is theta, therefore this angle is theta over 2, and this is also theta over 2. Okay, so what is the mass before? 30. Actually, let's solve for the cosine that we need. So cosine theta over 2 is mv over 2 times m prime v prime, and the mass before is 35 grams, and the velocity before is 0.4. And then after we have 2 times 37 grams times the velocity after, which is 0.21. Notice that I am not using kilograms and I use grams, and this is because you are dividing grams with grams, so that's fine because they cancel out. So this gives you 0.9, which means that theta over 2 is 25.72 degrees. So theta is 51.45 degrees. Okay, and that's the answer. Question 13. So this was an okay test, I think, but let me know in the comments if you thought that this was a difficult test or an easy test. So question 13 gives you a total of 3 marks, so it should take you 3 minutes. So that's the rule of thumb. If it takes you 5, that's fine. Don't freak out. Don't become a timekeeper or a police officer of yourself. Okay, that's not good. But just have it in the back of your minds. So a student placed 2 magnets on a top pan balance. The student clamped a metal wire horizontally in the uniform magnetic field between the magnets as shown. The student connected the ends of the metal wire to a battery, an ammeter, and a switch. When the switch was closed, the reading of the ammeter was 3.1 amperes. The reading on the balance increased by 0.45 grams. The length of the metal wire in the magnetic field was 40 millimeters. Calculate the magnetic flux density in the region between the magnets. So this is a classic case where we use FB. So if you have a current carrying wire inside a magnet, and actually in this configuration in which the current is this way and the magnetic field is perpendicular to it, so that's your current and that's your magnetic field, then the force on your wire is equal to the magnetic flux density times the current times the length of the wire inside the magnets. Okay, and since your top pan balance showed this reading, it means that this must be equal to m times g. Okay, and you simply solve for b. Okay, so b is 0.45 times 10 to the negative 3, so I'm converting grams to kilograms. Actually, let me take an intermediate step because maybe it's confusing. So let me solve for b first. So b is m times g over IL. So 0.45 times 10 to the negative 3 kilograms times 9.81 over the current, which is 3.1, over the length of the wire in the magnetic field, which is 40 millimeters, which is 40 times 10 to the negative 3 meters. We get this cancellation to find that B is 0.0356 Teslas. Okay, and that's the answer. Right, question 14. This is one of my favorites because I like particle physics. So The omega minus baryon was discovered in 1964 when a negative count meson K minus was observed to collide with a stationary proton. The omega minus was produced in the following reaction. K minus plus proton gives you omega minus plus K plus K plus K0. State the quark structure of a meson. Mesons consists of a quark and an anti-quark pair. Okay, that's it. Explain how the law of conservation of baryon number and the law of conservation of charge are obeyed in this reaction. So let me write it down again. K minus plus a proton goes to omega minus plus a kaon plus a neutral kaon. So let's examine the charge. So we have -1 plus 1 equal to 0 before, and then after we have -1 plus 1 plus 0, which is equal to 0. So we have not momentum, sorry, we have charge conservation. Now about the baryon number, only the proton has a baryon number, so we have 0 plus 1 for the baryon number before, and then omega minus is stated to be a baryon, so it has a baryon number of 1, and then kaons are mesons, so they have 0 baryon number, so we have a baryon number of 1 after, so the baryon number is conserved. Okay. Before its discovery, I jumped to part B. Before its discovery, the mass of the omega minus was predicted to be 2.9714 times 10 to the negative 27 kilograms. The most recent accepted value for the mass of the omega minus is 1,672 MeVs per c squared. Calculate the percentage difference between these two masses. So there are two ways to work this problem out. You can convert MeVs to MeVs over c squared to kilograms, or kilograms to MeVs times c squared. So in our case, we're going to convert these to kilograms. So the predicted mass, sorry, the accepted mass, not the predicted, is 1672 MeVs, which means 10 to the 6 electron volts, and 1 electron volt is 1.6 times 10 to the negative 19 joules over 3 times 10 to the 8 squared. And this works out to be 2.9724 times 10 to the negative 27 kilograms. Okay, so the difference between the accepted and the predicted is simply 1.044 times 10 to the negative 30 kilograms. So the percentage difference is delta m over m accepted times 100. And if you plug in the numbers, you're gonna get 0.035%, which is an excellent agreement. Whoever predicted this value, he was spot or she was spot on. So that's great. Okay. There is a part C to this question. The photograph shows tracks produced by particles in a particle detector when a K minus collided with a stationary proton. The tracks produced by the K plus and omega minus are labeled. Explain how evidence from the photograph shows that a K0 was also formed. Okay, I'm gonna show it to you visually. Can we use white? Yes, okay, it works. So I'm gonna use white color. So here, notice how you have this K minus coming in. Somewhere here it hits the proton, I guess. And then you have an omega minus moving that way. K plus moves almost in the same direction as the K minus was moving before, which means that the omega minus has a component of its momentum in this direction, and then a momentum of its, a component of its momentum in the vertical direction. That component, this one, needs to get balanced out by something else, by another component here maybe. Okay, and then another component here. So you probably have a particle moving in that direction called K0, okay? and that's how they predicted it. I'm going to erase all this because it's confusing maybe, and I'm just going to keep this one. So there is evidence that there is a particle moving in that direction, and it doesn't leave tracks because it's not charged, okay? And that's there to conserve, so let's call it K0. And that's there to conserve momentum. And how do we write this down? Because it's a writing problem. K naught is needed for momentum conservation actually full stop. It's responsible for balancing the momentum of omega minus, and we can also add that K0 is neutral, so it leaves no tracks. Okay, that's the answer. Now let's move to question 15. A turnable is a circular board that rotates around a vertical axis. Dining turnables can be used on large tables as shown. They have a glass of water and a dining turnable and a large table. The turnable is used to move the glass of water to different positions. The photograph below shows the side view of the glass of water on the turnable. Okay, fine. The turnable is rotated through 160 degrees as shown. The time taken for the turnable to be rotated around through 160 degrees is 2.2 seconds. Show that the average angular velocity of the glass is about 1.3 radians per second. Okay. So how do we do that? Remember that omega is defined as the change in angle over time, but angle has to be given in radians. Okay, so we have 160 over 2.2, but we need to convert degrees to radians. How do we do that? We multiply by pi over 180 degrees. Why is that? Because pi radians is 180 degrees. And if we do this calculation, we find 1.27 radians per second, which is very close to 1.3 radians per second, which is quoted there. Right. The glass can be placed at different positions on the turntable. What's wrong with me today? Explain why the angular velocity of the glass is the same, but its velocity varies depending on the position of the glass on the turntable. So the simplest way to see it is that V is omega times R. So the velocity varies with respect to the position from the center singular, not plural. There is only one center in a circle. Okay, from the center of the circle. And that's it. Part B. The maximum frictional force between the glass of water and the turntable is equal to mg over 30, where m is the mass of the glass of water. Someone says that if they place the glass less than 5 centimeters from the edge of the turntable, then the glass will slide when the turntable rotates. Deduce whether they are correct, and they give you the angular velocity and the diameter of the turntable as 50 centimeters. So how do we approach this? So pretty much if you have a turntable and maybe this is your glass over there, there has to be a centripetal force which is provided by the frictional force. Let's call it F, lowercase f, which is the friction. And that frictional force, Ff, is equal to m omega squared times r. Okay, so we simply have to solve for r, F frictional over m omega squared, and they quote that they don't give us the mass, but they tell us that that's equal to, that the frictional force is mg over 30, and then we have m omega squared, so the masses get cancelled nicely, and we can just plug in 9.81 over 30 times, and then omega squared is 1.3, and then square it, don't forget to use parentheses, and we find 0.193 meters. But notice that this is 19.3 centimeters, right? And the radius of the circle is 25 centimeters. Minus 19.3 centimeters gives us 5.7 centimeters, which is larger than 5 centimeters. So that's okay. I mean, it works. The statement is correct. Okay, hope this makes sense. And the final question in this question 15, two identical glasses are placed at the same distance from the edge of the turntable. One of the glasses is filled with water and the other is empty. Explain whether either of these glasses will be more likely to slide as the turntable is rotated. Okay, so remember that that the force of friction was given to us as mg over 30, and then the maximum radius is equal to the frictional force over m omega squared, and if we combine this, the radius is g over 30 omega squared, independent of mass. Okay, so the probability for them to move is equal. So the probability is equal. Or in other words, the radius at which they slide is independent of their mass, actually. So it doesn't matter. Okay. Next question, question 16. So we have a 6-mark long writing problem about accelerators. So the simplified diagrams show a LINAC and a cyclotron. Both machines are used to accelerate charged particles. Explain how these machines use a potential difference to accelerate charged particles. Okay, so let's start answering this. 6 marks means that you have to provide about 1 point that proves or answers the question. So 1 sentence or 1 point per mark. So in both machines, there is a voltage that creates an electric field, let's call it E, which accelerates the particles. So that's our first point. Now the polarity in both machines, meaning that this is the polarity, plus or minus, and then it switches into and minus and plus, and then plus and minus, and so on. So the polarity in both machines constantly switches so the particle is always accelerating. So that's the second talking point. The third point could be that acceleration only happens in between so in between the D's or the tubes. Okay, so these are the D's. Okay, they're called D's because they look like the letter D. Okay, so this is the D's, or inside the tubes where the electric field is, pretty much. Okay. The frequency of the AC voltage is constant in both machines. The time, and the final point could be that the time needed from the between, sorry, I confused myself. So the time needed from when the particle exits the acceleration point, the acceleration part, the acceleration space, okay, that's better, and it enters it again, is the same. Now this is a confusing point. Let me try to illustrate graphically. Hopefully I will explain it. So let's take the cyclotron. Is this a good example? Yeah. So the idea is that you have, let's use blue. You have an, actually let me use a clean page. Maybe it's gonna be better. Okay, let me use a clean page. So this is the first D. Let me use black. So here and here, and this is the first D, and this is the second one. Okay, so you have a particle accelerated in this space. So let's say it moves to the left. Okay, and then it enters this space in which it's not accelerated, it's only bent by the magnet. Okay, and then it enters this acceleration space again, and it's accelerated this way, and then it again travels this way all the way there. So the time needed t, if the time needed to go from point 1 to point 2 is t, then the time needed to go from point 3 to point 4 is also t. Okay, and this is because the time, the frequency of the AC voltage is constant. Okay, so it needs to take the same time to travel. So it travels a larger distance here in this part because it has a higher velocity, pretty much. Okay, and this is the final point. I hope this was clear. So I'm sorry, I don't know why it glitched like that. Part B. A scientist plans to use each type of particle accelerator to accelerate protons from rest. I. In the LINAC, a potential difference of 0.4 megavolts is applied to the tubes. The protons pass through 4 gaps. Show that the speed of the protons is about 2 times 10 to the 7 meters per second as they leave the 4th gap. Okay, so the work done on a charged particle of charge q inside some potential difference v is simply q times v. Okay, and the kinetic energy it acquires is 1/2 mv squared. So let's try to make that v a little bit different. Okay, so these two have to be equal, pretty much. So 1/2 mv squared has to be equal to the charge of what is it? Protons. So the charge is E, right? Times the accelerating voltage times 4, right? Because and the reason why I said 4 is because there are 4 gaps. Okay, so let's solve for V. So V is simply 8 times E times this acceleration voltage over the mass, and this is square root. And if you do the calculations, you find 1.75 times 10 to the 7 meters per second, which is about 2 times 10 to the 7 meters per second. Okay, part 2. In the cyclotron, the protons leave the Ds when the radius of their path is 29 centimeters. Deduce whether the speed of the protons as they leave the cyclotron is the same as the speed of the protons as they leave the fourth gap in the line, and they give you the magnetic flux density. So in this case, this is kind of useful because they are talking about this part over here. Okay, so this is circular motion. So in circular motion, QVB, the Lorentz force on the charged particle, must be equal to mv squared over the radius. Okay, so this v gets cancelled, which is nice. So velocity is qbr over the mass. Okay, and I'm not gonna plug in numbers again because I feel a little bit lazy. I'm sorry guys, but you can use your calculator. If you plug the numbers in, you will find 1.53 times 10 to the 7 meters per second, which is less than 1.75 times 10 to the 7 meters per second. So no, they are not the same. They're kind of close, but not the same. Right. Question 17 starts with this semi-intimidating graph. Okay. The output of a power supply varies as shown, and they show the potential difference versus time. A capacitor can be connected to the power supply to modify this output. As the output increases, the capacitor charges. The capacitor modifies the output and produces the variation shown by the bold line on the graph below. So this part, which I'm going to delete. State the potential difference across the capacitor at the end of a period of discharge. So this is a period. So this point and this point and this point, to me it reads to be between 3.5 and 3.6. So I'm going to state it as 3.55. Okay, volts, because they give you volts. Okay, simple. And you see that this is 1 mark, so it took me 1 minute, less than a minute. So that was an easy problem. Part B. The capacitor discharges through a resistor labeled with a value of 6.8 kilo ohms and a tolerance of plus or minus 5%. The capacitor has a capacitance of 3.3 microfarads. Deduce whether the output with the capacitor shown on the graph is consistent with a resistor tolerance of plus or minus 5%. So for this, we will use V is equal to V naught E to the minus T over RC, which applies to a discharging capacitor. So for this part, from here all the way down here, and then again from there to there, or from there to there, or whatever. So we can use any two voltages along this graph. So I'm gonna use, let me erase everything because I messed the graph up. Okay. So we can take V naught, the initial voltage, to be 5, and then we can take the final voltage to be this guy over here. Okay. So between this part and this part, 5 milliseconds passed. So that's the change. So first, let's make it a little bit easier. So ln of V over V naught, actually ln of V is ln of V naught minus T over RC. So ln of V over V naught, remember that ln of X minus ln of Y is ln of X over Y. Okay, so ln over V naught is minus T over RC. So we want to calculate R. So ln, what is the voltage here? 5. What is the voltage there? 4. I chose the values because it's the simplest. So 4 over 5 is minus 5 times 10 to the negative 3 seconds, which is the time elapsed. Okay. over the R, the resistance we want to calculate, times it, capacitance 3.3 times 10 to the minus 6. So this logarithm is minus 0.22, and to the left we have minus 15.15, 1515 over 0.15. So both are negative numbers, so R is positive 6.71 kiloohms. Okay, 6.71 kiloohms times 0.05, which is 5%, is 0.3 kiloohms. So what was the question? Deduce whether the output of the capacitor shown on the graph is consistent with a resistor tolerance of plus or minus 5%. So it is consistent. Okay. Part 2. Calculate the change in the energy stored in the capacitor during the discharging process. So the discharging actually starts here and ends there. So it starts with 5 volts and ends with 3.50, let's say 3.5 volts. Let's use that. Okay. So what's the energy stored in a capacitor? 1/2 C times V squared. So the change in energy is 1/2 C times V initial squared minus V final squared. We can use 5 volts there and 3.5 volts there to find 2.1 times 10 to the negative 5 joules. Now the resistor is replaced by a bulb with a much lower resistance than 6 kiloohms. Explain why the output is now very similar to the original output of the power supply. And what's the original output? Let me erase everything so you don't get confused. So the original output is this one. Okay, I'm gonna erase it. So how do we reply to this question? The time constant is R times C. So the new time constant is gonna be equal to the new resistor times C. So T prime is gonna be less than T. And since V is V naught e to the minus T over RC, the discharge will be much faster. Okay, and the capacitor will start charging again fast. So what's gonna happen, pretty much, I'm gonna illustrate it. So the capacitor will charge really fast like this, okay, and then it's gonna discharge fast. So here it takes some time to discharge, but in the new scenario where the capacitor the resistor is lower, it's gonna discharge fast like that. Okay, and then it's gonna start charging again, and then discharge fast. Okay, so the new output is gonna look very similar to the actual output. I hope this makes sense. If it doesn't, please ask me in the comments. And I would like to move to question 18. Some mobile phones can be charged using a wireless charger. To charge the mobile phone, the charger is connected to a power supply. The mobile phone is placed near to the charger as shown. Okay, there is an alternating current AC in a coil in the charger. There is a second coil of wire in the mobile phone. A diagram of the charger and mobile phone is shown below. Okay, so they show you that there are two coils pretty much. Okay, and the phone charges. Explain how the mobile phone charges when placed near the charger. So the answer is simple magic. Okay, so we answer magic. Believe me, guys, I have been doing this job for a long time, and I've seen some crazy answers like that in physics papers, even at the highest level. No, not the highest level, maybe the level of undergraduate level. Okay, so okay, let me get serious. Okay, how do we answer this? This is a 4-mark question, so we have to provide about 4 points. Okay, for sentences that prove the concept. But okay, the answer is the AC current in the primary coil. The primary coil creates a magnetic field B in the primary coil with a direction that changes with time. Basically, if this is the coil, the current goes this way, so the magnetic field is out of the page. If it goes that way, and because it's an alternating current, it switches to the other direction, in which case B changes and it goes inwards, and this repeats indefinitely pretty much. Okay. All right. Now, this was the first point. The magnetic flux linkage in the secondary coil changes with time, and the magnetic flux linkage is n, the number of turns, times the flux, the magnetic flux, which is B times A. Okay. Okay, that was the second point. From Faraday's law, mth is equal to minus delta n phi over delta t. Thus, the change in the flux linkage n times phi gives rise to an induced EMF. Okay. Since the coil is a closed loop, a current runs in the coil and charges the phone. Oops. All right, that's the answer. So we have 4 points. I think we answered it completely. Let's move on. B. A teacher demonstrated a simplified version of the charger to her class. She used 2 identical coils. She attached one coil to an AC supply and the other coil to a digital voltmeter. The magnetic flux density produced by the coil connected to the AC supply has a maximum value of 18 milliteslas. Calculate the maximum magnetic flux linkage for the coil connected to the AC supply. The diameter of coils is 4 centimeters. The number of turns in each coil is 50. All right, so we have to calculate the magnetic flux linkage, which is n times phi, and phi is B times A, and A is pi d over 2 squared because they give us the diameter. Okay, so I'm gonna plug the numbers in this time, even though I still feel lazy, but anyway. So 50 turns, 18 times 10 to the negative 3 teslas, pi is 3.14, d is 4 centimeters, so d over 2 is 2 centimeters, so 2 centimeters is 0.02 meters squared, so this is 1.13 times 10 to the negative 3. Do you remember the unit used to measure flux linkage? It's Weber, WB. All right. Last question. The maximum potential difference across the coil connected to the digital voltmeter is less than the maximum potential difference of the AC supply. Suggest why. So the maximum potential difference across the coil connected to the digital voltmeter is less than the maximum potential difference. Okay, suggest why. No iron core connecting the coils might be a reason, or the coils are far away, so some linkage, flux linkage, is lost. I cannot think of anything else, to be honest. So let's move on. It's 1 mark, and we wrote down 2 points. Less is more in general, but in this kind of tests, more is better, meaning that better to be safe than sorry. So it's okay if you write 2 points down. So anyway, 19 and last question. In desert areas of California, solar panels use sunlight to generate electrical power. If the sun collects on the solar panels, their efficiency is reduced. To remove sand, a positive electric charge is given to the sand particles and a negatively charged plate is moved across the panel. The diagram shows a negatively charged plate above a positively charged solar panel. Add to the diagram to show the electric field lines between the plate and the solar panel. So this is your negative, this is your positive side. So the field goes from the positive to the negative, and it's perpendicular to these plates, equally spaced. And that's the answer. Now, a positive electric charge is given to the sun particles when the solar panel is charged. When the negatively charged plate is moved across the solar panel, the sun particles move off the panel, as shown below. Okay, explain why a sun particle moves as shown. So it flies. No, that's not the answer. So the proper way to answer it is that an electric field E is set up between the charge plate is set up. We don't have to write that. Pushing the charged particles up along the direction of the electric field, pretty much. They move up because the force, which is Q times E, is larger than their weight, which is M times G. And that's the answer. Okay, 2 points. Show that the electric field strength between the negatively charged plate and the solar panel is about 8.1 times 10 to the 5 volts per meter. They give you the distance between plate and solar panel and the potential difference. So that's a simple problem, actually. So E is V over D. Let me check if they give this formula back in the back where they give you the equation. So here it is, V over D. Okay. So V over D, you just have to plug in numbers. So you get 8.13 times 10 to the 5 volts per meter, which is about 8.1 times 10 to the 5 volts per meter. So that's fine. Okay, the maximum positive charge that can be given to the sun particles when the solar panel is charged is 4 times 10 to the negative 12 coulombs. The table below shows the diameters of some sun particles. Only some of these particles will be lifted from the solar panel when using an electric field strength of 8.1 times 10 to the 5 volts per meter. Deduce the largest diameter of sun particles given in this table that could be lifted from the solar panel, and they give you the density of the sun. Okay, so for anything to happen, we need Q times E to be larger than or equal to the mass of the sun times G. Okay, but what's the mass of the sun? We don't know, but they give us the density. So for one sun particle, we need Q times E to be larger than or equal to the mass is equal to the density times the volume times G. Okay, so Q times E have to be larger than or equal to what's the volume of a sphere, 4/3 pi, and then they ask for diameter, so let's use D over 2 cubed, okay, which is the volume of a sphere times G. Don't forget the G. Okay, so if you rearrange everything and solve for D cubed, 2 to the cube is 8, so you get that D cubed has to be lesser than or equal to, and why is it lesser? Because D is on this side of the equation, so it has to be less than whatever is on the left hand side. Okay, so if I bring it to the right hand side, it has to be lesser than or equal to 6 times Q times E over pi times rho times G, and we have to take the cube root of that. And if we plug in numbers, we will find 6.23 times, 0.7 micrometers. So the largest particle that will be lifted is this one, 590, okay? Because this one is too large, so it's not lifted. And the same goes for the other one, obviously. So, part C. The solar panels are usually inclined at an angle theta to the horizontal. The plate moves parallel to the solar panel as shown. So, add to the diagram below to show the forces acting on a charged sun particle. So, this is not something to scare you. It's basic physics pretty much. So, we have the mass of the particle always perpendicular. Okay, so mg, and then you have Q times E, and the electric field is perpendicular. Okay, so the electric field is in this direction. So QE is in the same direction as the electric field, and mg is vertical. Okay. And final question, explain how inclining the solar panel at an angle theta would improve the removal of sun particles from the solar panel. So if we go back to this diagram, pretty much we can analyze the weight, okay, into mg cosine theta, because if this angle is theta, then this angle is also theta. Why? Because this side is perpendicular to this side, and then this side is perpendicular to this side, so the inscribed angles have to be equal. Okay, so now QE has to lift the mg cosine theta component of the sun's weight. So that's actually a little bit better, okay? There is, of course, this component mg sine theta, which just makes the particle move in that direction, the direction I show with the arrow here, but that doesn't really matter, okay? And this was 2025's Unit 4 walkthrough. Let me know what you think about the way I solve these papers, the way I teach, and the plan is to keep putting things out. And eventually I'm gonna put out some machine learning tutorials and stuff like that. So that's totally unrelated to high school, but I'm gonna be talking about things I like in this channel. So like and subscribe, tell your friends, and so on and so forth. See you in the next one. Bye.